cooking apprentice stands at the stove. She tastes the dish, that's fitting the data. She checks the recipe, that's obeying the physics. If the dish tastes right but she baked at -50 degrees, the recipe says something is wrong. A physics-informed neural network uses both signals, match the observations and satisfy the governing equations. The loss function is the sum of tasting and reading. A pure data-driven neural network has no knowledge of physics. Train it on drug concentration data, and it might predict negative concentrations at some time points, physically impossible. Give it sparse data, 5 measurements over a month, and it hallucinates wild oscillations between the data points. It needs enormous amounts of data to learn what a first-year pharmacology student knows. Concentrations are non-negative, elimination is roughly exponential, steady state requires input equals output. Physics gives these constraints for free. Data-driven models must learn them from examples. A pure mechanistic model, the ODE system from the plumbing network or your GBM dashboard, encodes known biology directly. The equations define how compartments interact, how drug is cleared, how tumors grow. But mechanistic models have parameters that must be estimated from data. When data is sparse, a few clinical measurements over months, some parameters are non-identifiable. Your GBM QSP model has 13 coupled ODEs and 3 non-identifiable parameters KGM prolif, KERK activate, and KKIXKR internal. Profile likelihood analysis confirmed, they can't be pinned down from available data alone. The textbook is incomplete. The PINN bridges both worlds. A neural network Q of T approximates the solution. The loss function has 2 terms. Data loss, at the measurement times through Tn, the network output should match the observed values. Mean squared error, just like standard regression. Physics loss, at many additional time points, collocation points, the ODE residual should be 0. Compute dot from the network, plug into the ODE, and penalize any non-zero residual. Total loss equals data loss plus lambda times physics loss. Lambda balances the two. The key enabler is automatic differentiation. The neural network output U of T is a composition of differentiable functions, linear layers and activations. High-Tucker jacks can compute dot with respect to T exactly. No finite differences, no numerical errors. This is the chain rule, computed automatically by the framework. Plug the exact derivative into the ODE, dot minus f of u and parameters should equal 0. The physics residual is computed analytically, not numerically. No Euler method, no work. The neural network is the ODE solver. You have 10 clinical measurements over 6 months. Traditional fitting. 10 data points constrain 10 equations. Everything between measurements is unconstrained. PINNs evaluate the physics loss at 1,000 randomly sampled collocation points between the measurements. At each collocation point, the ODE must be satisfied even though no data exists there. The physics constrains the solution everywhere, not just at observations. The recipe tells the apprentice how the dish should evolve between tastings. The trajectory between measurements follows the ODE, regularized by physics. Data loss fits the observations. Physics loss enforces the ODEs. Autodiff provides exact derivatives. Collocation points fill the gaps between measurements. The apprentice uses both the tasting and the recipe. Next, how PINNs solve your specific modeling problems.